All right, guys, welcome back to our ENCOR class. We are now moving into our routing protocols. We're going to be talking about 3 different types of protocols over the next couple of days. We're going to start with EIGRP, the Enhanced Interior Gateway Routing Protocol. And then we're going to get into some OSPF, Open Shortest Path first, and then we'll get into some external BGP. So starting with EIGRP, EIGRP is kind of one of the original, more modern routing protocols that we see in use in networks today. It was born from EIGRP, which was really the very first interior gateway protocol that was developed even prior to RIP. But EIGRP had some serious limitations that really made it kind of a protocol that wasn't used too much beyond its years in the beginning. The biggest limitation of EIGRP was the fact that it was a classful routing protocol, meaning that it did not do subnetting, it didn't do variable length subnet masks, it didn't support summarization, all of the modern things that we need for routing protocols today. So EIGRP came out in the early 90s. It was released as a Cisco proprietary routing protocol, and it was classless, meaning that it supported all of those things like subnetting and summarization and authentication and variable length subnet masks and so on. So we're going to kind of do a bit of a deep dive into EIGRP. As you can see there, it was released in the late 90s, the early 2000s. That's when we also saw the use of OSPF for IPv4. And we're going to focus our attention with EIGRP on EIGRP for IPv4, even though the modules that EIGRP includes actually work very well with IPv6 as well. All the theory that we're going to discuss, specific to the algorithm, which is dual, the diffuse update algorithm, all the theory that we're going to discuss pretty much is the same for IPv4 and IPv6. There's really not a whole lot of difference. The protocol pretty much acts the same with regard to successors and feasible successors and feasibility condition and how EIGRP selects the best path in the routing process, etc. So even though we're going to focus our attention on IPv4, we're pretty much learning how EIGRP works with IPv6 as well. Even the implementation is very similar in with the protocol itself. All right. EIGRP in July of 2013, I believe it was released as an open standard. Prior to that, it was Cisco proprietary, but released as an open standard to the public with some limitations. Some of the enhanced features of EIGRP are still considered to be proprietary, but most of the basic features of EIGRP were released as an open standard in RFC 7868. You can go Google that and download that RFC and see what features are supported as public features in public domain, if you will. So other vendors, if they choose, like Juniper and HP and whatnot, can choose to implement EIGRP on their platforms with the code that Cisco's released for open use. All right, we're not going to take a look at that RFC because we're going to pretty much focus on the functions of EIGRP, regardless of whether or not it's the open standard versions or the proprietary components of EIGRP. So what are some of the basic functionality, what are some of the basic concepts of EIGRP, right? Cisco does retain control of EIGRP. Most of its enhanced features like stub routing, stub query scoping, the ability to control kind of scalability features, if you will, of the protocol still remains somewhat proprietary. But the basic implementation, establishing adjacencies, sharing routing information between peers, that kind of thing has been released as an open standard. Now we see in the diagram here that EIGRP has some specific components, and we'll probably talk about each of these components in detail, but I'm going to break down some of these components while we're on this diagram here, just to give you an idea of what some of the features are of EIGRP and how it might differ from other kind of widely used interior gateway protocols like OSPF, for example, because there are some significant differences between those protocols. Some similarities, but a lot of differences. Start with load balancing, right? Most IGP protocols, which would be ISIS, OSPF, EIGRP, even RIP, have the ability to load balance if the paths that are included are equal, right? So if we have network paths that have the same metric, regardless of whatever metric that might be, it could be hop count or it could be overall path cost, as long as the metric is the same, we have the ability to load balance those paths, meaning that multiple paths can be put into the RIB, the global RIB, not the protocol RIB, but the global RIB, and we can utilize those paths at the same time. Could be a per packet load balancing type of scenario, some sort of method of monitoring load balancing so that we are, kind of equally using those paths that have the same metric. But the one unique aspect to EIGRP that is different than any other routing protocol is its ability to do what we call unequal cost load balancing, where it can actually insert into the global RIB routes that don't have the same metric. And this is something you guys are familiar with. I mean, you learn about EIGRP from day one when you start your Cisco training, and everybody kind of talks about this, the ability of EIGRP to do this unequal cost load balancing. So how does that work? Well, we use a function in EIGRP that is associated to something called variance. And I'm sure that we'll see an example of variance a little bit later on as we get more in depth into this chapter here, or into these chapters here. But it is the only protocol that has the ability to do this unequal cost load balancing. OSPF, in order for us to load balance paths, they have to have the same metric. We either have to trick OSPF into thinking they're the same, or they actually literally have to be the same, right? In ISIS, it's a very similar concept. BGP, as an exterior routing protocol, actually doesn't even support load balancing. We can do kind of fake load balancing, if you will, by manipulating path attributes and then forcing. So, sorry about that. So, we'll talk about the load balancing aspects with BGP as well when we discuss, BGP path attributes and how we can kind of manipulate different BGP paths to route between autonomous systems. But load balancing is a very easy component of EIGRP. It's very easy to do. And we'll talk about how we insert what we call multiple successor routes into the global routing information base by manipulating paths in EIGRP, or manipulating what we call the feasible distance of a path, or the variance itself. Reduced bandwidth usage. I'm going kind of counterclockwise here because the last one I want to talk about is a little bit different. But reduced bandwidth usage means that EIGRP is more efficient than a traditional distance vector routing protocol. I don't know that we'll get into the differences between distance vector and link state in this particular case with this particular courseware, but there are significant differences between a link state routing protocol, which would be OSPF and ISIS, and a distance vector routing protocol, which would be traditionally EIGRP, and RIP, right? Distance vector routing protocols traditionally did periodic updates, which meant that they would send out updates every X number of seconds. RIP would be every 30 seconds, and EIGRP would send out updates every 90 seconds. But the only time we actually really should ever have to send out an update is if something changes in the topology, right? Or if there's a new link comes up or a link goes down. Those are the only times we should really have to change or propagate information about routing, because everything should be stable and not really changing much, right? So what they mean by reduced bandwidth usage is that EIGRP does the triggered and incremental updates as opposed to periodic updates. So it only sends out routing updates as an update. It's an actual EIGRP packet type. When something changes, or when the topology changes, or if a metric changes, or anything, or any kind of network reachability information changes. That's why oftentimes EIGRP tends to be classified as an advanced distance vector routing protocol, because it does take a lot of characteristics from link state in order for it to be more efficient and operate more efficiently. All right. Classless routing. The classless routing concept, very, very important. There were a couple of different RFCs that were released fairly early in the 80s. 1981, I believe it was, is when IPv4 was really kind of standardized and became kind of a global standard, right? And it was very quickly after that they realized, hey, this whole classful concept, meaning that we have Class A, Class B, Class C, Class D, and Class E. This whole classful concept is not going to scale well to the global internet. We're going to have too many subnets, we're going to have too many users, and being able to stay within the class boundaries by defining a specific subnet mask for each class is just not going to work. EIGRP was written after the classless interdomain routing RFC was published, which means that when they developed EIGRP, they made it a classless routing protocol. What does that mean from a usability perspective? It means that EIGRP uses, or advertises, I should say, subnet mask information along with the routing updates. So because we're sending subnet mask information within the routing updates, we don't have to assume what the subnet mask is going to be. We can just simply read the subnet mask information in those updates when network reachability information is being advertised. Means is that as I send out routing information, I'm sending out my subnet mask information, and I don't have to worry about staying within the classful boundaries. From an implementation perspective, what that means is that now we have the ability to do things like route summarization. We can do things like summarize at different points within the network, meaning we can take a bunch of smaller subnets and we can advertise them as a larger subnet to reduce the size of our routing information base and to add efficiencies in the convergence process of the protocol. Or we also have the ability to do other things like speed up convergence time of the routing protocol, because we're not trying to advertise as much information. So if there's a topology change in the network and we're summarizing routes at a certain point within that network, the summary route's not going to change, which means that other routers within the topology don't have to run their algorithm, they don't have to try to reconverge, and it just makes the protocol much more efficient. All right. Now, it used to be by default when you implemented EIGRP that it still acted classfully. There was a command that was executed by default prior to the 15 code release, where, and you guys have probably seen this command before, the auto summary command, right? Where EIGRP would automatically summarize to major classful boundaries, even though it was a classless routing protocol. We don't have to worry about that anymore, because now by default, any kind of modern operating system is going to have that feature turned off by default, so we don't have to worry about disabling that feature with a no auto summary command. Unfortunately, we're probably not going to see too many EIGRP configuration examples in this courseware, but I'll bet you in the advanced routing feature or section, we'll see a lot more about the configuration and implementation stuff that we would hope to see in this section here. But all right, now loop free, very important concept within EIGRP, and it's probably one of the most difficult concepts to capture when you're discussing the theory of EIGRP is how does EIGRP provide a loop-free topology? Okay, one of the biggest limitations of a distance vector routing protocol is that it doesn't have the ability, or doesn't provide us the ability of, or visibility, I should say, of the entire topology. A link state routing protocol exchanges detailed information about the state of every link in the topology. What routers are connected to what subnets, what is the cost of those links, etc. So as I start to build my reachability database within within OSPF, I have a complete picture of the topology, right? And that's kind of the whole concept of link state. The link state database is like a complete roadmap of the entire physical topology. In a distance vector routing protocol, I only advertise the routes that I'm using. So let's say router 5, for example, has 3 different paths to reach network X. Okay? Router 5 has 3 different paths to reach network X. It chooses one of those paths based on a metric. Well, when router 5 decides to advertise network X to its upstream neighbors, it doesn't advertise to the upstream neighbors the 3 different paths that it has. It only advertises to the upstream neighbor the path that it's using. So by the time I get from router 5 to router 4 to router 3 to router 2 has very little information about the overall topology because it's doing what we call routing by rumor, meaning that it's making its routing decision based on the routing decision that the neighbor made, and then that neighbor is making its routing decision based on the decision that the other neighbor made, and so on. Does that make sense? Hopefully it's still a good choice, right? Hopefully my neighbor made the best choice to route, and their neighbor made the best choice to route, and so on, and we're still choosing an optimal path. But the point is that we don't have a complete picture of the topology. That's really the biggest point, right? With a distance vector routing protocol, you don't have a complete picture of the topology. Okay? So that being said, in order for us to ensure that we're not causing a loop in the topology, or that a particular path that we're choosing to route with isn't a loop in the topology, we have a whole bunch of other things that take place in order for us to guarantee that a primary path and even a backup path is loop free, meaning it doesn't, the backup path does not include parts of the original routing path. A diagram would be much better. Hopefully we'll see something a little bit later, and I might go back and kind of revisit this topic. But you guys may have heard this before, right? You have your metric in EIGRP is what we call the feasible distance, right? The feasible distance is essentially the metric that we use to measure the overall cost to reach a destination. The path with the lowest feasible distance becomes the successor. Right? The successor is the path that goes into the routing table. It also goes into the topology table, because everything we learn in EIGRP goes into the topology table, but the successor goes into the routing table. Now what EIGRP does, and actually this is something that is kind of better for the protocol than what we traditionally see with like OSPF, is EIGRP not only chooses the best path to reach a particular destination, but to speed up convergence, And to identify what to do if the primary path fails, EIGRP chooses the second best path as well. Or it tries to confirm, if you will, a second best path. And that second best path is called the feasible successor. Right? But there's a condition that gets checked in order to confirm that that second best path is loop free. And that's called the feasibility condition. We'll probably see it a little bit later on. I'll describe what it is right now, but I don't expect you guys to remember it just based on what I'm saying, because these concepts, these dual concepts that we're talking about, really do require us to kind of look at it visually, and I'll draw a diagram and kind of represent these concepts a little bit later on as well. But the feasibility condition basically states that if the reported distance of the backup path. So I've chosen my primary path, we'll just call it A. And let's say the metric of A is 10, okay? The overall path metric, the feasible distance of the best path is 10, right? So that's my primary routed path. But I do have an alternate path. And what EIGRP does is says, okay, let's go ahead and identify this as an alternate path. So if the primary path fails, I can go ahead and use this alternate path immediately. But let's make sure, because we don't have a complete picture of the topology, let's make sure that this alternate path is loop free. So we're going to do a feasibility condition check, which states if the reported distance of the backup path, reported distance is the cost for my neighbor to reach the destination, not the overall path cost, but the cost for my neighbor to reach the destination. If the reported distance of that path is less than the overall feasible distance of my primary path, then there's no way that that alternate path can include my primary path. Mathematically speaking, there's just no way that the alternate path could include my primary path. That is what they talk about, this loop-free topology. I know it's confusing as hell, but again, we'll get into it a little bit later on, and I'll probably utilize some sort of diagram to kind of demonstrate the concept. Right now, I'm just kind of hitting the high points of the protocol right now. All right. So basically, the whole concept of loop-free means that we're doing these checks to verify that alternate paths are loop-free. And it's based on some specific math that we implement in the algorithm itself. Multi-address family is another interesting concept. We actually used to teach this as part of the CCNP route switch class. It was one of the final EIGRP lessons that we did. It's not required to configure or what we call named mode EIGRP configuration, but we had the ability to combine both v4 and v6 configuration options by using a named mode configuration. Now, there were other reasons to go and choose named mode over classic EIGRP configuration. The biggest difference was we had the ability to use what we call wide metrics. We went from a kind of a 8-bit wide, or I'm trying to think if it was 8 or 16-bit wide metric to a 32-bit wide metric. But the idea being that we had much faster links in modern networks than we had traditionally in the 80s and 90s. So the metric field, the actual field that carries metric information, wasn't large enough to differentiate between, say, a T1 and a 100 terabit link or a 100 gigabit link or whatever. So we would have to move over to the named mode configuration so we had additional space to store that metric information. We might get into that concept a little bit later on. I'm not sure if we will or not, but if we don't see it here, we'll most certainly see it when we get into the advanced routing piece. All right, very quick to converge. If the protocol is designed correctly, right? Convergence in any routing protocol is a factor of multiple things. The protocol itself inherently has designed in it rapid convergence functionality, right? OSPF, more modern routing protocols tend to have relatively quick convergence times. But convergence is not just a matter of what protocol you choose. Convergence is also a matter of how you implement the protocol. Are you implementing summarization? Are you implementing other techniques that the protocol provides? For EIGRP, for example, it would be like query scoping, where you're limiting where queries are sent to avoid having to send out queries and get replies if routes are lost, right? These are all elements of increasing the efficiency of the protocol. In OSPF, for example, we would increase the efficiency of the protocol by implementing a multi-area design with ABRs, and then having those ABRs provide a place for summarization and so on. So when it comes to convergence, it's a very, very important concept. And EIGRP is actually one of the fastest converging protocols, even faster than OSPF, if it is designed correctly. Okay. Load balancing, like I said, equal and unequal cost, loop-free classless routing. EIGRP sends mask information along with the network information and supports things like discontiguous subnets, meaning that we're not doing major classful summarization. We can do no summarization at all if we choose, or we can summarize to kind of smaller subsets of networks that might not include the whole class. So that's very useful. Multi-address support. In this case, they're talking about the ability for EIGRP, the packet modules, if you will, to support things like AppleTalk and IPX. We don't really care about those protocols. But certainly the ability to do dual stack is important, right? The protocol has the ability to do not only IPv4 routing, but also IPv6 routing. And most of the concepts, most of the framework that's built for v4 is easily extensible over to IPv6. Reduced bandwidth usage, we talked about that as well. One thing I didn't mention about the bandwidth usage, though, is traditionally with traditional routing protocols like RIP and IGRP, we would use broadcast addresses to exchange routing information. With EIGRP, we use a multicast address. Specifically for IPv4, that's going to be 224.0.0.10. And in IPv6, it's going to be FF02:A, which is the equivalent of 10 in hex. So very, very efficient routing protocol. And I've got some captures here. When we do our deep dive, I'll show you some captures and maybe talk a little bit more about how messages are exchanged between routers in the concept of in the context of EIGRP. So what are three characteristics of EIGRP? It is not a classful routing protocol. It is classless. It does support IPv6. So it is a dual stack protocol. And the solution distribute dial plan information for VoIP networks. Yes, we do have that ability. It's called the Service Advertisement Framework. We probably won't get into that too much in this class. If you were going to do the CCNP collaboration, you might see some more about that. But it does have that capability, and we only mention that in this case because unified communications is typically something that we do see quite a bit of in most modern networks today. Now, as a protocol, EIGRP runs directly on top of IP. OSPF and EIGRP are the only protocols actually ISIS, I believe, also runs on top of IP, but RIP, the Routing Information Protocol, and BGP, interestingly enough, are application layer protocols. You know, they allow us to exchange routing information, what we call network layer reachability information, but BGP runs on top of TCP, and RIP runs on top of UDP. So actually, within the context of the OSI model, those protocols are really classified as application layer protocols. EIGRP and OSPF they get their datagrams get encapsulated directly inside of IP. So there is no transport layer function, right? There's no TCP or UDP function with EIGRP or OSPF. EIGRP uses protocol number 88. So what does that mean? That means that in the packet header, there's a field specifically in the packet header. In fact, let me go to my Wireshark capture here. There's a field specifically within the packet header. Well, this is all v6, but that's okay. We'll open this up. In the packet header called the protocol field, or in the case of IPv6, it's been renamed to the next header field. And you can see the value of that is 88, meaning that that's how we identify the protocol. ICMP is protocol 1, OSPF is protocol 89, EIGRP is protocol 88, and so on. So there is no transport layer function for this particular protocol. Now, why is that particularly important? Well, that means that we cannot rely on transport layer reliability mechanisms like sequencing, acknowledgements, three-way handshake with TCP, you know, all of the flow control mechanisms that TCP provides and so on. That has to be built into the routing protocol, and EIGRP actually has that functionality built in it. If I go and look at an EIGRP packet header, you will see that within the packet header that we actually have sequencing and acknowledgement numbers built into the packet header. There's basically 5 major packet types that exist in EIGRP. But every single one of those packet types includes a sequence field and an acknowledgement field. So the reliable transport, that reliability is built into the protocol itself. A lot of people talk about it as RTP, the Reliable Transport Protocol. And it's a little bit misleading because a lot of people think that there's kind of this secondary protocol that gets implemented when you implement EIGRP. But RTP is really just a function of EIGRP. It's part of the sequencing and acknowledgement elements that are included in the EIGRP packets themselves. So we're not running a separate actual RTP protocol on top of EIGRP, if that makes sense. Okay? So we know that EIGRP has some reliability built into it. And it's built directly into the packets themselves. We also know that it uses a multicast address. EIGRP can use multicast for adjacencies. It can use multicast to disseminate routing information, but it can also use unicast. There are scenarios in which EIGRP packets are sent as unicast packets in certain network topology types and so on. But certainly never as a broadcast, right? Like IGRP and RIP did back in the day. RIP version 1 anyway. All right. It also says EIGRP runs directly above the IP layer as protocol 88. That means that when you look at a packet capture for EIGRP, you're going to see a layer 2 header, you're going to see a layer 3 header, and then you're going to see your EIGRP packet header. The EIGRP packet header actually is consistent across both v4 and v6. It's consistent across every packet type. And we can actually see the packet header fields here. There's a version field. There's an opcode, which tells us, is this a hello packet? Is this an update? Is this a query? Is this a reply? Is this an acknowledgement? So this opcode will tell us what kind of packet type is being sent in EIGRP. There's a checksum, so that's for file or message integrity and data integrity. There's some various flag fields, sequencing acknowledgement, virtual router information. We'll talk about VRFs later on. And then finally the autonomous system number, which we'll talk about. Very, very important concept in EIGRP, that autonomous system number. All those fields that I just highlighted are part of the EIGRP packet header. It's just kind of a standard set of fields that is included in every single EIGRP packet type. What follows that is the actual payload information. So in this particular case, this is a hello packet, and this is the payload for the hello packet. An update or a query, if I go back to my list of packets here, if I go to an update, for example, you'll see that you have the same kind of fields in the header, right? Let me expand this. You see the same kind of fields in the header, but then you'll see the payload information is different. So this is an update, which means that we're advertising information about prefixes. In this case, v6 prefixes. So every EIGRP packet has a fixed header, and then it carries that specific EIGRP payload information. All right. Now it says here also, only selected packets are sent reliably, requiring acknowledgement upon receipt. There are 5 major packet types that EIGRP has. There's actually about 8 or 9 different packet types in EIGRP, but there's 5 major packet types that the protocol has. A hello packet, which is used to establish adjacencies between EIGRP peers. An update packet, which is used to propagate routing information, reachability information. Usually updates are sent during the initial convergence process. A query packet, and a query packet is used to request routing information. Queries are only sent if the primary route fails and I don't have a backup route. A reply packet, which is a response to a query, and an acknowledgement. Those are the 5 major packet types in EIGRP: hello, update, query, reply, and acknowledgement. Some of these packets are sent reliably, which means they're sequenced and they're acknowledged. A query, an update, a reply, those 3 packet types are always sent with sequence numbers and they're always acknowledged. A hello packet is not acknowledged and it's not sequenced, and an acknowledgement is not acknowledged and it's not sequenced. That kind of makes sense. If you acknowledge acknowledgements, you'd never stop, right? So that's what they mean by that with regard to selected packets are sent reliably, specifically hello, updates, and queries. Stuck and active queries are also sent reliably, but for the most part, we only really focus our attention on the 5 major packet types. Unlike RIP, but like every other major routing protocol, EIGRP establishes a formal adjacency prior to exchanging information. Okay? So that means I am not going to exchange routing information. I'm not going to exchange updates, or I'm not going to send queries unless you are a formal neighbor of mine. All right? We call that an adjacency. And EIGRP routers and OSPF routers are very similar. They form adjacencies prior to exchanging any information. Those adjacencies are established using the hello packets within EIGRP. Now, what does a hello packet include? Let me switch over to v4 cap. So as I was mentioning, I wanted to capture or get a sample capture of some v4 packets here, because we were looking at v6 before. But you can see in the info field here, we see our hello packets, we see our updates, we see an acknowledgement. Hellos and acknowledgements have the same opcode. That's why one has hello ACK and one doesn't have hello ACK. This is actually an acknowledgement to an update. And I don't know that we see any queries here or replies, but we see at least 3 of the major packet types in this list here. And notice the destination address is 224.0.0.10. In the packet header, the layer 3 packet header, the protocol field is 88, as I mentioned. But if I then go and look at the EIGRP payload, or the EIGRP packet header, notice this looks exactly the same as v6. That's the wonderful thing about v4 versus v6 information. The protocols pretty much operate exactly the same way. So when you learn about EIGRP for IPv4, you're learning about EIGRP for IPv6 as well. So what is it that's actually inside this hello packet that allows us to form the adjacency? Well, there are specific parameters that are included. The type, we use what we call type linked value fields, TLVs. TLVs I always kind of equate to like a Tupperware container, right? Type is what type of container is it. Length is how big is the container. And the value is what's inside the container, right? So we use these TLVs to carry information within EIGRP. In this case, the type is parameters, and then this is the size, type, length, and then these are the values, right? So the type of the container is a parameters container, the length is 12 bytes, and then this is the actual information that's contained within the container itself. These happen to be K values, and K values are used to manipulate the metric for EIGRP. And they're very important, even though Cisco says don't ever change the K values. Each of these K values correspond to a component of the metric. So K1 is bandwidth and K3 is delay. And then K2, K4, and K5 have to do with reliability and load. But the critical thing about the K values is that they have to match in order for EIGRP routers to be able to form an adjacency. The K values have to match. So this is one of those set of parameters that we're going to be confirmed between the peers before they can form an adjacency. Another component of the parameter section is the hold time, right? Hold time is how long I'm going to wait, right? Let me actually back up and start by saying we establish adjacencies by sending out periodic hello packets. Anything that's sent periodically means that it is sent on a specific time interval, right? And there's a couple of different timers for EIGRP. In any kind of broadcast network, like an Ethernet network, the hello timer is 5 seconds. So every 5 seconds we're sending a hello packet. And the dead timer, or what we refer to here as the hold timer, is how long I'm going to wait. Once I've established an adjacency with a peer, how long am I going to wait if I don't get a hello from that peer before I decide that that peer no longer exists, right? Because there's an adjacency table or an adjacency database called the neighbor table where this information is stored. So you become my neighbor, I put you in my neighbor table, and you become a routing information source for my routing information. Well, you might go away. The link to you might fail, or you might disappear, or otherwise not be running EIGRP. I'm not going to keep you in my adjacency database forever. At some point, I have to decide that you don't exist anymore, and I have to remove you, and everything that you taught me needs to be removed. That's what the hold timer is for. The hold timer allows me to identify that a peer no longer exists, and I need to remove that peer and any information that that peer shared with me, right? That's what that hold timer value is for.
Enough sharing, Scott.
Sorry about that. My WebEx was acting a little bit weird. But anyway, what you're seeing on the screen here is a really, really critical picture. Not only for EIGRP, but for OSPF, for BGP, because all of these protocols have very, very similar structures. There are three major components to any routing protocol. And if you really want to become an expert in these routing protocols, you need to understand these three critical elements. Number one, message types, right? What are the messages that the protocol uses to exchange information, right? When I say messages, I'm talking about like a hello packet, a query, a reply, an update. Those are EIGRP message types. In OSPF, it's a hello, a link state advertisement, a link state acknowledgement, a database descriptor packet. In BGP, it's an open message and a keep alive and so on. So every routing protocol has different messages that they use to manage the adjacencies and to manage the exchange of information between the protocols. So as you learn these routing protocols, as you try to become an expert in these protocols, you need to investigate and understand what each of these different message types are and how they're used and what their purpose is and what function they're providing. That's number one. Number two is what we call data structures. Data structures are tables or databases that store information. And we can see three specific data structures that are listed on this slide: a neighbor table, a topology table, and a routing table. Well, each of these data structures store information that's relevant to the protocol. The neighbor table stores adjacency information. Who are my neighbors? What are the properties of those neighbors and so on. The topology table stores everything that I'm learning from my neighbors. So not only the best routes, but the next best routes and the third best routes and the fourth best routes and so on. And then the routing table is basically just my global RIB, right? My global routing information base. So that's not specific to the protocol. It is, more importantly, just kind of attached to the router itself. But that is my routing information, right? That's the routes that I'm using, which then gets used to construct, my forwarding information base and so on, if I'm using Cisco Express forwarding. Well, guess what? OSPF has a neighbor table. OSPF has a topology database. We call it a link state database in OSPF. OSPF has routes in the global routing table. BGP has a neighbor table. BGP has a topology database. BGP has routes that go on the global routing table. So that's the second of the three that I was that we identify as kind of really important to understand if you truly want to understand the protocol. Any idea what the third thing is? Right? The third thing is the algorithm. How does the protocol make decisions? In OSPF, it's Dijkstra's algorithm, or what we call the shortest path first algorithm. In EIGRP, it's dual. In RIP, it's Bellman-Ford. BGP uses, we don't have a specific name for the algorithm, but we certainly have a process that we use to make decisions. And those are the 15 or so different path attribute selections that we make: weight and local preference and AS path and MED and so on, right? So if you're going to learn about any routing protocol, you need to focus on those three aspects. What are the messages that we use? What are the data structures that are constructed for the protocol to function? And what is the algorithm that the protocol uses to make decisions? So anytime I teach a protocol, I always kind of focus on those three aspects of the protocol. And we try to kind of become experts in those three elements, if you will. And that's what we kind of break down for each protocol. So what you're seeing is a progression here, right? You're saying, okay, the first step is to establish an adjacency. We do that with hello packets. That information goes into our adjacency database. There are certain parameters that have to match in order for us to become peers, right? Certain parameters within the hello packet itself or within the configuration of the protocol for us to become peers. With EIGRP, those parameters include things like the autonomous system number has to match. Authentication, if you're running a routing protocol authentication, the authentication properties have to match. The routers need to be in a common subnet. That's very important as well. The K values have to match between the peers. The timers don't have to match. In EIGRP, the hello and dead timers don't have to match. They can be negotiated, and so on. In OSPF, the timers do have to match. So when we go through each of these protocols, we talk about these different kind of things that are important for the protocol. Once I've established an adjacency by exchanging hello packets and becoming neighbors, then I send routing update information, right? I tell you everything that I know, you tell me everything that you know, and that information gets compiled into my topology database. The topology database is the specific rib for the protocol. Remember I said yesterday that we have two different routing information bases. We have a routing information base for the protocol, which is basically the topology table. And then we have our global routing information base, which is the actual routing table on the router itself. So if you want to see the protocol specific rib, you would do something like show IP EIGRP topology, or show IP OSPF database, or show RIP database. If you want to see the global routing table, the global rib, if you will, the global routing information base, you would type show IP route or show IPv6 route. And that's what would allow you to see the global routing information base. Does that make sense? The key here, guys, is that there's always this progression of convergence. And more importantly, when you're trying to troubleshoot these protocols, if you understand how that progression works, right? You understand that, hey, I am not going to get information in my topology database if I don't have any adjacencies, right? So it doesn't make sense to start troubleshooting my topology information if I haven't already verified my adjacency table, right? My neighbor table. And that's how we kind of focus on our troubleshooting effort, is we kind of go down the line here. Let me make sure I have all my neighbors first. If I have all my neighbors and I'm still missing routes or whatnot, let me investigate the topology database, because maybe I've got some interfaces that are not running EIGRP that should be, or whatever. So they should show up in the topology database if they're running EIGRP, and so on, right? And then you finally start to troubleshoot your actual routing information. So it makes it much, much easier to kind of verify the operation of the protocol once you've identified specifically how that protocol works, right? And I'm going in way more in depth in this than what the book provides, because I just think that the book just doesn't talk about it enough, you know, to give it really a true understanding. So, I mean, this diagram is pretty basic, right? Hey, I'm router 1. Hey, router 1, I'm router 2. Great, let's become neighbors. Well, it doesn't say anything about K values have to match, and you know, an autonomous system number has to match and all that, right? So, but we are seeing all those pieces that I talked about. We're seeing the message types, we're seeing the data structures, and we're not necessarily seeing the algorithm specifically, but it's there as well. All right. Now they do talk about the algorithm a little bit in the description here. The successor route, for example, these are terms that are specific to EIGRP. OSPF and RIP and ISIS don't use these terms, but the successor route in EIGRP is the best route. That's what goes into the topology table. That's what goes into the global RIB, right? The global routing information base. Maybe, right? What would prevent a successor from going into the global RIB? Any ideas? We know it's the best route within EIGRP. But just because it's the best route within EIGRP doesn't mean it's the best route on the router, right? We have things like administrative distance that allow us to identify whether or not route A or route B goes into the table. EIGRP usually wins that battle, right? Because it has the lowest overall administrative distance of all of my IGP routing protocols. But maybe I have a static route, or maybe I've modified the administrative distance of OSPF, so OSPF routes are trusted more than EIGRP routes. Who knows? But just because...
Depending upon how large your EIGRP system is and how many devices you have in it, sometimes you'll get external EIGRP routes that are in your routing table that will also cause that.
Yeah, absolutely, because external EIGRP routes have an administrative distance of 170, whereas OSPF routes have an administrative distance of 110. Let me explain that a little bit, even though it's not part of this topic. It's pretty important, right? There are multiple ways that routers decide what route they're going to use. And it depends on certain characteristics. So let's say, for example, I have 3 routes in my routing table. One is 10.0.0.0/16. And then I have another route, 10.0.0.0.0/18. And then I have another route, 10.0.0.0/20. Okay. They all look very similar, right? As far as the actual prefix, it's the same, but the prefix length is different for each of them. It's very possible that I could have a packet that comes into the router that matches all 3 of those routes. You know, a packet of 10.0.0.1, for example. I'm sending a packet to 10.0.0.1. It actually matches all 3 of those routes. Do you guys know which route would ultimately be used in that case? It doesn't matter if it's OSPF or EIGRP or BGP or whatever. What route ultimately gets used in that case?
The more specific?
Right, the longest match, right? The one that has the longest prefix length that still matches the packet. So that's one of the kind of tiebreakers, if you will, within the routing table. We use longest match routing, and administrative distance doesn't come into play there because they are unique routes. They're not the same route. Now, on the other hand, if I learn about the 10.0.0.0/16 route from EIGRP, and I learn about the 10.0.0.0/16 route from OSPF, that's when we have a tiebreaker. Both of those routes cannot go into the routing table. We have to decide, are we going to put the EIGRP route in the routing table, or are we going to put the OSPF route in the routing table? And that's where administrative distance comes into play. Administrative distance is a tiebreaker for trustworthiness of the routing information source. And in Cisco speak, there are some very specific AD values that you probably should be familiar with. Connected routes have an administrative distance of 0. Static routes have a default administrative distance of 1. External BGP routes have an administrative distance of 20. Internal EIGRP routes have an administrative distance of 90. OSPF 110. ISIS 115. RIP 120, and external EIGRP 170, and then internal BGP 200. So those are some of the common ones. The lower the number, the more trusted the source. So going back to that example, 10.0.0.0/16 from OSPF and EIGRP, assuming I'm using the default administrative distance values, the EIGRP route would go into the routing table. Okay? But that only comes into play if it's the exact same route, same prefix length from 2 different information sources. The third decision factor is simply metric, right? If I learn about the 10.0.0.0/16 route from 2 different EIGRP sources, then I'm simply going to choose the path with the lowest feasible distance, the path with the lowest metric. And that becomes my successor. That's what goes into the routing table. All right? I love teaching routing because there's just so many interesting pieces to it, right? It's just a very interesting concept. Feasible successor, the best alternate loop-free backup path to reach the destination. All right. Now, I already kind of talked about this a little bit, but let me see if I can go ahead and, since they're mentioning it here in more detail, let me go ahead and see if I can create a diagram here real quick. In fact, I don't need to create a diagram. Let me pause my video and pull up something real quick. So I wanted to pull up this diagram because it kind of makes it easier to visualize what these algorithm concepts that we talk about with EIGRP. A very simple diagram. I use this in all my classes to describe the whole feasibility condition concept, right? Router 1 can reach network X through 2 different paths. It can go through router 2 or it can go through router 3, right? Now, router 1 does not understand what the entire topology looks like. We can see the whole topology ourselves, but because this is a distance vector routing protocol, router 1 only knows that it can get to network X through either router 2 or router 3, which is the vector, with a specific metric, which is the distance. It doesn't know what sits beyond router 2 and router 3. All right, we can see what sits beyond router 2 and router 3 because we have a complete picture of the topology. But as a protocol, EIGRP doesn't see that. EIGRP doesn't understand the whole topology. Feasible distance, which is the green arrows, represents the overall path metric for the protocol. So that's feasible distance is just a term that we use in EIGRP to describe the overall path metric. And we'll talk more about how the metric is calculated. We use a complex metric in EIGRP, which involves K values and various elements like bandwidth and delay and reliability and load. But we're just using some basic numbers here. So the top path has an overall path metric of 2,000. The bottom path has an overall path metric of 2,500. Well, whichever one is lowest is going to win, and that becomes my successor path. So the path through R2 becomes my successor route. That is the route that ultimately would go into the global routing information base, as well as the EIGRP routing information base. So we've got our routing path, right? And again, that's pretty straightforward. We're gonna take this path to reach network X, and most protocols like OSPF and RIP, that's all they do. They just choose the best path, and they don't worry about creating some sort of alternate path. Now in OSPF, there is something called LFA, loop-free alternate, which is exactly what we're going to describe here when we talk about the feasible successor in EIGRP. It's basically OSPF LFA is implementing a feasible successor type of implementation within the protocol so that we can do faster convergence and so on. It's not something that exists by default, but you can configure it. So EIGRP, in order to achieve much faster convergence in the event that the primary path fails, EIGRP will attempt to automatically calculate a loop-free alternate path, which is what we call the feasible successor. All right, that's what we call the feasible successor. But in order for that path to qualify, it has to meet the feasibility condition. Okay? And the feasibility condition states that the reported distance of the feasible successor needs to be less than the feasible distance of the successor. This is the feasible distance of the successor. This is the reported distance of the alternate path. Does that make sense? Reported distance is the distance for my neighbor to reach the same destination. That's why it's called reported distance. It is the distance that's being reported to me by my neighbor. Does that make sense? In this case, 1,500 is less than 2,000, which means that the path through R3 qualifies as a feasible successor. Now, what does that mean from a convergence standpoint? That means that if router 2 were to fail, or if this path were to fail, we would immediately start routing to router 3 as a loop-free alternate without having to run dual, without having to recalculate, without having to send a query, etc. Basically, it's just kind of like we've calculated this backup path in advance so that if the primary path fails, we can immediately start using that backup path, as long as it meets the feasibility condition. Why does that number have to be less? Because I know that if that number is less, if that reported distance is less than the feasible distance of my primary path, there's no way that that backup path includes my original path, which is the whole loop-free concept, right? That's what we're trying to calculate. So this is the cornerstone, if you will, of the dual process. This dual algorithm is this feasible successor. So I'll just read what it says here. Hopefully it'll make a little bit more sense now that you've seen it kind of visually. But the feasible successor is the best alternate loop-free path to reach a destination. As it is not the least cost or lowest path, therefore it's not being selected as the primary path. And again, that makes sense, right? Because you still have to consider the cost of this link to consider the overall path metric. A lot of people say, well, wait a minute, if 1500 is less than 2000, then how come that didn't become my primary path? Well, because we're only basing it on the reported distance, not the entire path distance. We didn't take into account the cost of this link to reach the neighbor on top of the 1500, which in this case is 1000, which makes this path overall less preferred. Does that make sense? All right. Feasible successors are important because they allow the router to recover immediately upon network failures. And that is really what makes EIGRP an advanced distance vector protocol. Its ability to calculate this loop-free alternate path so that if the primary path fails, we can immediately start using that backup path. What happens if I don't have a feasible successor? Well, that's where the query process comes into play. If I don't have a feasible successor and the successor fails, I have to send a query. My neighbors have to send a query. Then their neighbors have to send a query. I have to wait for a reply. And then eventually I'll make a decision on whether or not that alternate path is still usable and still valid. Remember, the queries are there just to make sure that the paths are still there. We couldn't confirm that it was a loop-free alternate path, so it could have been a loop, which means that path may not be there if my primary path fails. And the query process is just a way for us to kind of confirm that. All right, that makes sense. All right. So I'm not going to break down these bullet points here, but basically all they're saying here is, hey, that we send our hellos. The hello packets allow us to form an adjacency. Once we've formed the adjacency, we send the updates to the peers. The updates are the routing information. We acknowledge those updates and so on, and that's that. We've become fully adjacent. In OSPF, it's a little bit more complicated. In EIGRP, you're either a neighbor or you're not a neighbor. In OSPF, there's multiple states of neighbor relationships. There's down state and knit state, two-way, start, exchange, loading, and full. So there's multiple kind of states that we progress through as we're forming our OSPF adjacencies. And we'll get into that later on when we get into our OSPF discussion. Okay? All right. As far as the packet format goes, just like I mentioned previously, these are the message types. Hello packets are used to discover and establish adjacencies. They're sent out every 5 seconds unless it's a non-broadcast multi-access network that's slow speed, anything less than 1.544 megabits per second. Then in that case, the hello packets are sent every 30 seconds. And the dead timer in EIGRP is 3 times. So 5 and 15 and 30 and 120. In OSPF, it's 4 times. The timers are different. It's 10 and 40 and 60 and 180. But no, 60 and... I can't remember what the slow speed link one is. And I believe it's... I know it's 4 times, so whatever the hello timer is, but we'll see that later on. Updates are used to convey routing information. Queries are used to request routing information, but only in the event that we lose our successor and there is no feasible successor. Queries are not sent if we have a feasible successor and we can immediately start using the feasible successor. A reply is a response to a query. Request packets we don't see too much. I actually don't usually talk about request packets, but if I need to get some more specific information from my neighbor, I can send out a request packet. And acknowledgements are just basic, packets that we use to acknowledge the receipt of information. Like I said, there's only certain packet types that are actually acknowledged. All right. Let's see. EIGRP packets are sent and reply packets are sent as queries. Yeah, we talked about that. EIGRP interacts with which three tables? Not an ARP table. Certainly the topology database. That is my routing information base for EIGRP. No such thing as a metric table. The routing table is my global rib, and the neighbor table is my adjacency database. These are the three data structures that we refer to when we talk about the protocol. And like I said, the other protocols are very similar, right? OSPF has a neighbor table, has a topology database called the link state database, and we have a routing table. BGP has a neighbor table, topology table, and routing table, and so on. So it's pretty important, that aspect. So the next thing we're going to talk about, we've already actually kind of talked about, which is what parameters need to match between peers in order for us to be able to establish an adjacency, all right? The AS number has to match. This is an arbitrary value that you choose. It's not like BGP where the autonomous system number has a specific meaning, right? Public versus private. In EIGRP, all ASNs are private, so you can basically choose whichever ASN you'd like, autonomous system number, but they have to match, right? And it's a number that goes from 0 to 65,535, and again, it doesn't really matter which one you choose. But if I'm going to form an adjacency with a peer, I have to share the same autonomous system number. And we saw that it's part of the original, part of the general packet header for EIGRP. It's actually the last field in the EIGRP packet header. K values have to match. The K values, like I said, are there's 5 K values, and they're used in the metric calculation. We'll see the metric. We'll have our metric discussion in the next section. But the K values have to match between peers, all right? And even though Cisco gives you the ability to change the K values by using the metric weights command under the EIGRP process, Cisco says don't ever change them. I guess when they developed the protocol originally, they wanted to give the engineers and designers a lot of flexibility in how EIGRP did its path selection. So they gave you an option of these K values. Well, K values it's an 8-bit field, which allows us to, in fact, let me show you that real quick. That's another kind of interesting thing about looking at stuff in Wireshark. You can always kind of tell how large a field is by simply highlighting the field. So if I highlight K1, you see that it's in the hex dump there, it's a 0, 1. Well, guess what? Those are hexadecimal numbers, which means they're 4 bits each, which tells me that's an 8-bit field. Now, because I know that's an 8-bit field, I know that what the range of the values can be, right? 0 to 255, from a decimal perspective, 0 to 255. So the K value is used, and we'll see this in the next section, but the K value is used as a multiplier against a component of the metric. So K1, for example, is tied to the bandwidth element within the EIGRP composite metric. And so I can place more weight on the bandwidth component of the metric as opposed to the delay component of the metric by changing the K1 value. I can make it maybe bandwidth twice as relevant, I guess, or twice as important in the calculation of the metric by changing the K value to 2, or 10 times as important by changing it to 10. Never really need to do it, though. In fact, Cisco says don't change the K values, because if you change the K values on one router, you have to change them on all the routers within the autonomous system, because those values have to match. All right? So K values have to match between the peers. Let's see. Common subnet. Yes. In the packets that are being sent, we would be able to identify whether or not we share a common subnet with the peer. Certainly we have to have a unique IP address if we're going to share information, but a router that has an EIGRP interface in a /24 subnet, even though it might have reachability, will not be able to form an adjacency with a router that has a /25 subnet mask. It's just something that the router does check, and you'll get some syslog messages indicating that there's that the routers do not share a common subnet, so they can't form an adjacency. Even if they have reachability, right? A 10.0.0.1 router with a /24 should be able to ping and communicate with a 10.0.0.2 router with a /25. Because even though they have a different broadcast address, they are still considered to be kind of in the same range or scope of addresses, but EIGRP is smart enough to recognize that the subnet mask doesn't match, so they're not going to form an adjacency in that case. All right. Additionally, if you're running authentication, so EIGRP, we have the ability to perform authentication. Not encryption, but authentication. We basically create a message digest of the EIGRP messages and send that along with the message in clear text. And then we verify the digest. But there's a secret key that's used as part of that process as well. And that's how we do the actual authentication. Obviously, if you're going to run authentication on one router, you're going to have to run it on the other router as well. And the key material and the authentication method has to match. We have MD5 authentication available, or no authentication, and some of the more modern iOSs even do secure hashing as well. All right. Anything else that might have to match? Nope, not that I can think of. I think they covered everything here. You know, a lot of times people will assume that the timers have to match, but those can be negotiated. They do mention here as well that passive interface is something that you have to consider, right? Passive interface is a way for us to suppress the protocol from running on a particular interface, even though it's part of the routing protocol, part of the routing process, right? So in other words, we have a network statement that includes an interface, which means normally hello packets would be sent out of that interface, but we've gone and made that interface passive in our configuration, which suppresses the hello packets from being sent out that interface, but it still allows that network to be included as part of the process, right? Well, if a passive interface is not sending hello packets, it means that we can't form an adjacency on a passive interface, which means that we can't exchange updates. RIP kind of is a unique protocol because RIP just blasts everything out regardless. There's no adjacency, no formal adjacency process in RIP. We just blast out our information, and if it gets there, it gets there. If it doesn't, it doesn't. And I don't care if I'm a formal neighbor with you or not, but in OSPF and EIGRP and BGP, we only exchange information with routers that we have a formal relationship with. And that means that we have an adjacency with. Well, if an interface is passive, I can't form an adjacency, which means I can't exchange information. Okay? Now, they mentioned a couple other things about in relation to OSPF. We'll talk about OSPF a little bit later on. Which two EIGRP parameters need to match for an EIGRP neighbor relationship to establish? Router ID. Actually, we didn't talk about router ID yet. But router ID is a concept that exists in all of the routing protocols as well. And it's a way to uniquely identify a router within the domain. Router ID is either manually configured or it's the highest loopback IP address of any active interface on the router or the highest physical IP address. Those are the three kind of incremental steps that we use to choose a router ID. But actually the router IDs need to be unique. They cannot match. In EIGRP, it doesn't play as much of a role as it does in OSPF. In OSPF, the router ID plays a very significant role. Area ID is a concept reserved for OSPF. So yes, the autonomous system number has to match. Timers do not have to match. We don't even advertise our hello timers. We only advertise our dead timer. I don't care how often you tell me hello. I care when you consider me to be dead. Right? Because I want to make sure that my timer, my hello timer is less than my than the dead timer. Otherwise, we'll never form an adjacency. So we saw that in the packet header that EIGRP sends the dead timer as part of the as part of the overall packet information in the hello packet. So if I go open up a hello packet here, we can see it's not part of the packet header, right? The EIGRP packet header, but it is part of the parameters in the hello packet itself. So we see it right here the whole time. And that is, as you can see there, a 2-byte field, right? 16-bit field. And we also identify the software version. I have seen scenarios, this is one of the things they didn't mention, where there's some incompatibilities with specific EIGRP software versions, and the adjacency won't form if that discrepancy exists. But it's pretty obscure because you'd have to be running a really, really old version of EIGRP for that to happen. So the hello timers don't have to match. K values definitely have to match. All right. So the next section that we're going to talk about is about the metrics for EIGRP. Metrics are obviously a way that we measure effectively the cost of a particular path. And then based on that cost, we make a decision on how which path is going to be the best path, right? RIP, the metric that we use for RIP is hop count. For BGP, we don't really use a metric. We use more of what we call BGP path attributes. It's a path vector protocol. It's not kind of a traditional routing protocol. But with EIGRP, we use something called a composite metric. And a composite metric is really kind of a complex metric that uses lots and lots of different variables to calculate the best possible path. And it can get a little bit complicated if you look at the metric just by itself without considering the formula, because there's so many different elements to the metric itself, right? There's bandwidth, there's delay, there's reliability, there's load. But when you break the metric down to its fundamental components, most of those variables kind of go away because of the K values that are used in conjunction with the corresponding values of the metric. So, for example, only K1 and K3 are in essence turned on, which means only K1 and K3, which correspond directly to bandwidth and delay, are used as part of the metric itself. So, fundamentally, the metric is what we use to choose the best path if we're only learning about that path from one information source, which is EIGRP, and we're just simply trying to choose the best path. All right, so the K values we can see listed here. K1 is tied to the bandwidth component. K2 is tied to the load. K3 is tied to the delay. K4 and K5 are tied to reliability. And K2, K4, and K5 within the formula are 0 by default, meaning they're not part of the formula. Now, if I look at the actual formula, pull up this document here, and I look at the actual formula, we can see that the formula is the metric is equal to K1 times the bandwidth plus K2 times the bandwidth divided by 256 minus the load plus K3 times the delay, all of that times K5 divided by reliability plus K4. And if that's not complicated enough, bandwidth and delay have their own kind of subformulas. Bandwidth is 10 to the power of 7 divided by the minimum bandwidth along the entire path in kilobits per second times 256, and delay is the sum of all of the interface delays in microseconds divided by 10 times 256. So if I was to put those into the formulas as well, we would see that we have, kind of a really complex metric with EIGRP. But again, it doesn't end up being that complicated, because if you negate all the components of the metric that are related to the K values that are set to 0, most of the formula simply gets ignored, right? Most of the calculation gets ignored, and we're only relying on, in essence, two values to calculate the overall metric, which is bandwidth and delay. So it ends up being that the overall path metric for EIGRP is bandwidth and delay. But there are a couple of things that I want to point out here that are really important when it comes to evaluating the path metric. Number one, only egress values on the interfaces are considered in the metric calculation. This also applies to OSPF, it applies to ISIS, it applies to EIGRP. Only the egress values are considered. So if I'm considering interface delays and I'm considering bandwidths of interfaces, I'm only looking at the outbound interfaces along the path to the destination to determine the overall path metric. Inbound interfaces have no effect. That means that if you're doing any kind of path manipulation, if you're doing some sort of traffic engineering and you're trying to modify the path selection based on modifying metric attributes, you need to only modify the egress interfaces. Also, there's no floating point math, meaning that if I say that an interface, for example, has a bandwidth, or the minimum bandwidth along the path is 1.544 megabits per second. So I say 10 to the power of 7, and then I divide that by 1544, which is kilobits per second, I get this number, 6476.6839, etc., etc. There's no decimal value in the calculation. I don't multiply this number times 256. I drop the remainder and I just use the whole number, and that's how the metric is calculated. So it would be 6476 times 256 would be the bandwidth component of the metric. So two very, very important concepts when it comes to calculating the metric. No floating point math, and only egress interfaces are considered in the formula. All right. So K1 is the bandwidth. It says the lowest bandwidth of the route. All right. So if I have 3 routers in a path, and between router 1 and router 2 there's a 10 meg connection, and between router 2 and router 3 there's a 100 meg connection, then the bandwidth that's considered in the formula is the 10 meg bandwidth. Right? It's the worst bandwidth along the path. Delay is a cumulative delay. And these are not practical values, these are theoretical values. So it's not the actual throughput of an interface that represents the bandwidth. It's the actual speed of the interface, like the actual speed of the interface. If it's a 10 meg interface, it's going to have a bandwidth of 10 meg, even if you're not getting 10 meg of throughput. Delay is based on serialization delay. How long does it take for me to encapsulate data and send it out the interface, right? Put it onto the wire, basically. That's a fixed value. We're not talking about propagation delay or processing delay, which would be variables, right? Variable components. If we were using variable components in the metric, we would never converge, because we would always have to be recalculating the metric of the path with these variables. All right, makes sense? So that's how the metric is calculated. Hopefully when we get into the advanced routing section, when we do ENA-RSI, we get into actually manipulating some of these values and kind of doing some dynamic calculations with some labs and so on. All right. So bandwidth is K1, the smallest bandwidth of all outgoing interfaces between the source and destination in kilobits per second. Again, the formula for bandwidth is 10 to the power of 7 divided by that value. That becomes the bandwidth value. The load we don't really care about, because we're not really going to be looking at load, and Cisco doesn't recommend changing the K values to make load part of the formula. The delay is the sum of all the interface delays along the path in tens of microseconds. Now, if you do a show interface, you will see those delay values listed in microseconds. So you'll add up all those values and divide by 10 to get you to tens of microseconds, and then that's when you then apply that to the formula. All right. All right. So with regard to EIGRP, the classic metric, and what they mean by classic metric is the narrow metrics using classic EIGRP configuration. Remember I said if we switch to named mode, which is address family mode, we're using wide metrics. So the formula is slightly different in that regard. Really, it's just the multiplier that's different, the 256 that's different. All right. The composite metric formula is used by EIGRP to calculate the metric value. The formula consists of coefficients, K1 through K5, which are called metric weights, metric-weights. We actually set those K values by using the metric weights command as part of the process. EIGRP allows for modification of that default composite metric by manipulating the K values up to 254 to scale the components of the metric. So for example, if I wanted bandwidth to count more than delay, I want bandwidth to count more than delay in the overall calculation, then I would go ahead and change K1 to have a heavier or a higher weight than K3, right? Again, not recommended. So the formula, they do have it listed here, 256 times K1 times the bandwidth plus K2 times the bandwidth divided by 256 minus the load plus K3 times delay times K5 divided by reliability plus K4. If K5 equals 0, then the second part of the formula is simply not used. We don't ever multiply by 0 because then our metric would always be 0. K4 and K5 are always 0 by default, so in essence that section of the metric calculation goes away. All right, the K values are carried in the hello packet. We saw that as part of our discovery in the Wireshark capture. Mismatched K values means that we will not be able to form an adjacency. We use the show interface command to see the actual values that are used in the calculation. Like I said, these are theoretical values. These are not practical values that are used in the calculation. So I see their bandwidth is 1544 kilobits per second. The delay is 20,000 microseconds. The reliability is 255 over 255. The load is 1 over 255 and so on. All right. How could I manipulate these metrics? Well, I could change the bandwidth of the delay or the delay of the interface. I can certainly change the K values to change how the metric is calculated, but again, Cisco says don't do that. But I could also change the bandwidth and delay of the interfaces. I could say this interface is not 10 megs, it's a gig. Or this interface is not 1.544 megabits per second, it's 1,000 megabits, or 1.0 megabits per second. Right, so and we do that under the interface using the interface configuration commands of bandwidth and delay. Now, those calculations don't just affect EIGRP. They could have an effect on other types of calculations like related to QoS and whatnot as well. So that's still something to consider when you're modifying those values. All right. The bandwidth is always specified in kilobits per second. The delay is always configured in microseconds, so not tens of microseconds. So when we configure it and when we do the show interface, we see it in microseconds, but for some reason in the formula, it's in tens of microseconds. That's why you have to divide the number by 10 when you're doing the calculation. All right. Show IP protocols will give us the ability to identify what the K values are in the calculation as well. Now, one of the things that I alluded to originally was that the metric field wasn't wide enough to store discriminating information to be able to identify the difference between a very, very slow speed link and very, very high speed links. Traditionally in the past, that wasn't an issue because we didn't have 40 gig links and 100 gig links and and terabit links and so on. We only had, maybe sub megabit and megabit interfaces and 10 meg interfaces and 100 meg interfaces and so on. So with more modern approaches, more modern network designs, we might see interface bandwidths that vary from very, very low values to very, very high values. And in that particular case, the metric field is just simply not large enough to differentiate between those different values. So what they did is they created this EIGRP wide metric feature to go from a 32-bit metric, remember multiply by 256, that means we're adding 32 bits, to a 64-bit metric, which then allows us to really gives us plenty of room to identify the difference between, say, a very, very slow link and a very, very fast link, up to about 4.2 terabits a second. If we get beyond that in the future, we might have to modify the protocol again, maybe go to 128-bit wide metric, right? And that'll just mean that the protocol is going to have to be modified to include that. All right. We didn't really change the formula too much. I mean, the calculation is still somewhat the same. We have a K6 value now, but K1 and K3 are still 1. K2, K4, and K5 are still 0. And they relate to the same values that they did before in the original formula, right? K1 times the minimum throughput, which is the bandwidth. K2 times the minimum throughput divided by 256 minus the load, plus K3 times the total latency, plus K6 times the extended attributes. So there is some difference in the formula. I doubt that you would be tested on any wide metric scenarios on the exam, but just know that they've kind of modified the protocol, if you will, to account for these faster speed links. Okay, so I'm not going to spend too much time talking about the actual formula and how it's calculated, but it is different than the original formula. Which metric does the K value of K1 correspond to when we're calculating the best path? Well, it's bandwidth, right? K1 and K3 are the only two values that are associated to values that we actually use in the calculation. K1 is directly tied to bandwidth and K3 is tied to delay. All right. So how do we do path selection? EIGRP path selection is a pretty basic concept. And again, this is something we've kind of talked about already. We talked about the overall path metric and what a successor is and what a feasible successor is and how we calculate the feasible distance. But path selection with EIGRP, can involve a couple of different things, right? For example, am I doing equal cost load balancing or am I doing unequal cost load balancing? How do I affect or create the use of unequal cost load balancing, right? So that's what we're going to talk about in this particular case. EIGRP, the first step in any EIGRP process is to go ahead and establish an adjacency. And we do that with the neighbor table, right? Once we've established that adjacency, then we can decide, what types of routes exist and how we're going to communicate that information from one router to the other. And that goes into our topology database, right? We talked about feasible distance. Feasible distance is the overall path metric, which is a combination of the cost for me to reach my neighbor plus the cost for my neighbor to reach the destination, which is what we refer to as reported distance or advertised distance, right? So I don't like to use the term advertised distance because the abbreviation for that is AD, so sometimes people get that confused with administrative distance. So I like to use the term reported distance to kind of define the metric that the neighbor uses to reach the overall network destination. All right, and you can see it listed here. They actually say, well, we can call it advertised distance or we can call it reported distance. I like to use the reported distance option just so that people don't confuse AD with administrative distance, like I said. So there are two things that allow us to determine the best path, right? The successor path, which is the path with the lowest overall feasible distance. How much does it cost for me to get to my neighbor? And how much does it cost for my neighbor to get to the final destination, right? That overall metric is the feasible distance, and that's what I use to determine which path is going to become the successor. And we already talked about the feasible successor as well, right? And that's what this loop-free path selection section is all about, talking about the feasibility condition and so on. So we'll review this one more time, even though we did go into this in quite a bit of detail in the previous topic, right? EIGRP uses the dual finite state machine to track all routes advertised by all neighbors with the topology table. All right, so yeah, that makes sense. The topology database is everything that I'm learning, right? Not only the best routes, but the next best routes and so on. We perform a route computation on all the routes to select an efficient loop-free path to all destinations, and we insert the lowest metric route into the routing table. So I build my adjacencies, that goes into my neighbor table. Based on that, I learn information from my neighbors, that goes into my topology table. And then I extract from the topology table the routes that I choose to use, which become my successor routes, and that goes into the global routing table. Makes sense. That's kind of the progression, if you will, of how everything works within EIGRP. It makes perfect sense. A router compares the feasible distances to reach a specific network, and then it selects the lowest feasible distance as the best path. We then submit this path to the routing engine for consideration. Unless this route has already been submitted with a lower administrative distance, we talked about that as well, because the routing engine is going to take into account administrative distance if I'm learning about the same path from two different information sources. The path will be installed into the routing table. Again, unless somebody else with a lower administrative distance value is telling me about the exact same path, I'll go ahead and install the route. The feasible distance for the chosen route becomes the EIGRP routing metric to reach that network, and that's what goes into the routing table. So in this case, I've got two neighbors from router C. Router C can reach the 10110 network through router B, or it can reach the 10110 through network through router A. Now the overall path metric for the path through router B is 2500. That's the feasible distance from router B. The overall feasible distance for the bottom path is 2000. All right, makes sense. So the bottom path is what's going to end up going into the routing table because it has the lowest feasible distance. The question that I have, which you guys should now be able to answer, is the path through router B considered a feasible successor? In this case, it is, isn't it? Because the reported distance from router B is 1500, which is less than the overall feasible distance of the successor path. The overall feasible distance of the successor path is 2000. The reported distance of the backup path is 1500. 1500 is less than 2000, which means it qualifies as a feasible successor. Make sense? All right. And by the way, that would show up in the topology database as a feasible successor. It doesn't specifically say, hey, this is a feasible successor, but if you do a show IP EIGRP topology, all you're going to see are successors and feasible successors. You will not see routes that do not qualify. There are other candidates, we call them candidates, route candidates, but they don't qualify, so they don't show up in the topology table using that command. There is a sub command that you can add called all-links. If I say show IP EIGRP topology all-links, then it will show me all the paths, even the ones that don't qualify as feasible successors in the topology database. So there is a way to see everything best routes, second best, or feasible successors, and other route candidates that don't qualify as feasible successors. All right. Hopefully when we get into our advanced routing piece, we'll be able to play around with that and see that in the configuration. So let's kind of break this down. EIGRP topology database contains all the routes that are known to by each EIGRP neighbor. Router A and router B sent their routing tables to router C, and that's displayed in the database. Both router A and B have routes to the 10.110/24 subnet and to other networks that aren't shown in the database. Router C has 2 entries to reach 10.110. The EIGRP metric for router C to reach both A and B is 1,000. So as far as reaching the neighbor, there's no difference. But again, we have to consider the overall path metric to reach the destination, not just the neighbor. So we add the 1,000 to the reported distance that comes from each of the other routers, and that results in the feasible distance of the path. So router C is going to choose the path with the smallest feasible distance, which is 2,000. That's what goes into the routing table. That is our successor. We then choose the backup route, called the feasible successor. If one or more feasible successor routes exist, we will have a tiebreaker, right? So let's say, for example, I've chosen my successor and I have 3 alternate paths, and they all meet the feasibility condition, right? So they all qualify technically as feasible successors. I don't make them all feasible successors. I compare the overall feasible distance of each of those 3 paths, and the one with the lowest feasible distance becomes the feasible successor. The other ones qualify as feasible successors, but they're not actually going to be used because they might have a higher metric, overall path metric, than the first one, right? If that makes sense. So let's say I have 4 routes to a destination. Obviously, the one with the lowest overall path metric becomes the successor. So I've got 3 remaining routes. Let's say they all qualify as feasible successors, then I would choose the feasible successor based on the lowest metric of those remaining 3 routes. Okay? If we don't have a feasible successor, then that's when the query process gets involved, and when we lose our primary path, we have to kind of try and discover if there is a secondary path, or at least verify whether that secondary path is still valid, right? Just because a path does not meet the feasibility condition doesn't mean it can't be used. It could potentially still be used. We just have to go through a secondary check before we can use it. All right. If the route via the successor becomes invalid, possibly because of a topology change or if a neighbor changes the metric, Dual, the diffuse update algorithm, checks for the feasible successor to the destination route. If a feasible successor is found, we immediately use it. We don't have to recompute the route, meaning we don't have to go from a passive state to an active state. Passive and active are terms that we use to describe the state of the routes in the topology database. A route that's passive is stable and converged. A route that's active means that the query process has been triggered and we're waiting for some replies before we can decide what to do. All right? And that's what they're saying here in the last sentence. A route will change from the passive state to an active state if no feasible successor exists. What's happening when I move into this active state is a query is being sent to my neighbors. And I don't think in this class we're going to talk about the query, this portion of the class, the ENCOR portion. We're going to talk about the query process. Hopefully in the advanced routing portion, we'll talk about the query process. But, if I don't have a feasible successor, I have to go and verify whether or not I even have a valid route. That's where the query process comes into play. All right. So in this particular example, EIGRP metrics are kind of simplified. The metric values are going to be much larger in kind of a standard environment. All right, and they're even talking about here, don't confuse AD with administrative distance. Completely different concepts. That's why I don't use the term advertised distance. I use the term reported distance so that there isn't any confusion when you're talking about it, especially if you're using the acronyms, right? In EIGRP, yes.
So sometimes when we are changing our metrics, every now and then we'll actually get equals. So you'll have the same advertised distance, and we'll end up with like almost like a load balancing. How often do you see that?
The same advertised distance or the same reported, the same overall feasible distance?
I believe it's the same advertised distance, or it's the same feasible distance, because we end up with links to the same location.
Load balance. Yeah.
Right. So we'll end up with, it's not where we want to do it, but someone will accidentally change the bandwidth commands and they'll be equal.
Right.
So it'll start doing load balancing instead of actually doing the proper distance.
Right.
Using one.
That is the problem with manipulating metrics manually, right? You could run into a situation where the links appear to be the same, even though they're not the same. And the only way to fix that is to not do that, right? There is another way you can force the router not to load balance. There is a command within the EIGRP configuration called maximum paths. And the default maximum path value for EIGRP for IPv4 is 4. So up to 4 paths will be load balanced by default if the metrics are the same. In IPv6, it's 16 paths by default, and it can go up from there. I think it goes up to 64 in IPv6, and it goes up to 16 in IPv4. You can actually go into the router, and you can say maximum paths 1. And what that will do is that will instruct the router to not do load balancing, even if the paths are equal. Now, that breaks load balancing, right? Because if you want to load balance with a maximum path of 1, you can't, right? But it would prevent that problem from occurring, where you're running into a situation where somebody's changing metrics and forcing paths to be the same, even though they're not the same. So by doing a maximum path of 1, you're saying basically, hey, don't do any load balancing for this particular path. Does that make sense? The only other choice you have, of course, would be to make sure that you're not manipulating. Change the metrics just slightly so that they're not quite the same, right? But it sounds like that somebody was changing bandwidths or whatever, delays or bandwidths for a different reason. Maybe it's to affect a QoS policy or whatever, and they didn't realize its effect on EIGRP. Sounds like that's what was happening. But the only solution is either make them different or turn off load balancing by changing maximum paths. Okay, in EIGRP, a successor route is which one of the following options? It's an alternate path, a possible path, a suboptimal path, or the best path. Successor is the best path. Okay? So as we talked about many, many times throughout this discussion, EIGRP is the only protocol that supports equal cost and unequal cost load balancing. Equal cost load balancing is turned on by default. Like I said, in IPv4, up to 4 paths can be load balanced by default. What if I have more than 4 paths? What if I have 6 paths that are equal, but my maximum paths command is set to 4? Well, EIGRP uses a tiebreaker to decide which of those paths it will put into the load balancing algorithm. I believe it has to do with MTU. It'll look at path MTU, and then if the MTUs are the same, it'll use some other mechanism. But if my maximum path value is set to 4, then it's only going to put 4 paths into as successors into the topology database based on that, right? Equal cost load balancing, up to 4 routes by default. It can be modified up to 16. 16 paths by default with IPv6 up to 64. But the maximum number of routes really depends on what that maximum path setting is set to. This is called ECMP, Equal Cost Multipath Routing, right? Where we have the ability to load balance across equal cost paths. This is not unique to EIGRP. OSPF does the same thing. BGP doesn't, because BGP is a completely different type of protocol. Unequal cost load balancing, which is disabled by default because of the variance command. We need to modify the variance command in order for us to be able to do unequal cost load balancing. And the default variance value is set to 1, which basically means you can only do equal cost load balancing. EIGRP is the only protocol that has this capability to support unequal cost load balancing. And the variance value can go anywhere from 1 to 128. So that's a pretty significant value. When you consider how variance is calculated, it's actually a multiplier against the metric of the successor. And these metrics are very large, right? A typical metric for an EIGRP route might be like 409,856 or something like that, 409,856. So if I put in a variance of 10, that would be 10 times that value. Anything between that value and 10 times that value would be considered equal. So variance is kind of like unequal cost load balancing with a sledgehammer, right? We're not making small changes, we're making big changes, or the variance command has a large effect, if you will. All right, but we'll talk about that. I'm sure we'll see the solution for providing that in this section here. All right, so the metric weights command, like I said, allows us to identify, not metric weights, a maximum paths command allows us to identify how many paths we're going to load balance over, and equal cost load balancing is pretty simple, right? If I have more than one path that have the exact same metric, then I'll just simply insert those paths into the routing table. Important concept here, though, all right? When we're doing ECMP, sorry about that, most routing protocols will do a per packet load balancing algorithm, meaning we're not load balancing based on flows, source destination pairs like ether channel and so on. We're load balancing based on just packets, packet count. One packet goes over this link, another packet goes over this link, and so on. And that gives us a pretty good load share across the links. But if you're running Cisco Express forwarding, where we're doing, that Boolean logic to identify which interface we're going over, much like we saw with Ether Channel, Cisco Express forwarding might choose to use one link much more heavily over another link based on how the math is calculated. So Cisco Express forwarding does not use per packet load balancing. It uses an algorithm to decide which link the traffic is going to pass over. So even though you might have equal cost load balancing, you're probably not going to get an equal share of bandwidth utilization across those links unless Cisco Express forwarding is disabled. And if you go out to Google and you search on Cisco Express forwarding breaks load balancing, there's multiple documents out there that describe that process and what some possible solutions are to fix that particular problem. Okay, so we're not going to get into that right now. Maybe we'll get into it a little bit later on when we get into the advanced routing section, but just keep that in mind, all right? Because it's kind of an idyllic description when we're talking about just the routing protocol doing per packet load balancing. So it says here, by default, Cisco iOS software applies load balancing across up to 4 equal cost paths for certain destinations, if the paths exist. Again, that's IPv4 only, not v6. With the maximum paths router configuration command, meaning that it's configured under the routing process, you can specify the number of routes that can be kept in the routing table. If we set that value to 1, that means you're only allowed to use one path. And the selection of the path, there's certain criteria that are used to decide which path is used. It's not just kind of arbitrary. There's a way that the router evaluates the equal cost paths and says, okay, I'm going to go ahead and use this path because of X, Y, and Z. It's somewhat obscure, right? It doesn't really, in the end, make much of a difference, but there is a tiebreaker. All right. Cisco routers support up to 16 paths for load balancing. And that, by the way, is again IPv4. Okay. So we see the syntax here to adjust the maximum paths. You go into the routing process and you simply say maximum paths and you specify the number. How do I do unequal cost load balancing? Again, only available with EIGRP. We use something called the variance command. We have two paths here, right? The metric or the feasible distance of the top path is 90. The feasible distance of the bottom path is 25. So clearly the bottom path is going to be our successor. All right. Now with variance, which is done under the router configuration mode under EIGRP by simply using the variance command, we specify a variance value. So 25, I would have to have a multiple of 4 in order to include the 90 as well, and consider 90 as part of the successor paths. Because the variance value is actually simply just a multiplier against the best metric. So if my best metric is 25, and I apply a variance of 2, that means anything from 25 to 50 would be considered equal. If I apply a variance of 3, anything from 25 to 75 would be considered equal. If I apply a variance of 4, anything from 25 to 100 would be considered equal. So by putting in a variance of 4, the router is going to say, okay, I can go ahead and put both of these paths in here as a successor, and I'm going to do per packet load balancing, but I'm going to do it on a 4-to-1 ratio, right? So in essence, and it's not quite this way, but in essence, I'm going to send 4 times as much traffic over the faster link than I would send over the slower link, but I'm still going to be able to use both links at the same time. Does that make sense? There is one very important caveat to this, though. Okay, one very important caveat, and that is if the path does not meet the feasibility condition, even though it falls within the variance scope. So if that top path that had a feasible distance of 90 did not meet the feasibility condition, it would not be included as a route because it doesn't qualify. Does that make sense? The packet would have to qualify in order to meet the feasibility condition. The packet would have to qualify first. Meaning that it meets the feasibility condition. All right. Doesn't matter if it falls within the variance or not. I'm only going to use it if it meets the feasibility condition. All right. We can see how that variance is applied. We go under EIGRP 100, specify the variance, which is just a metric multiplier. Very, very simple. Now, when you're dealing with numbers like 25, that's pretty easy, right? But when you're dealing with traditional EIGRP metrics like 409.2586 or something like that, applying a variance of even 2 is a pretty significant jump, right? Because 409.2586 times 2 is a much larger number than 25 times 2. Does that make sense? So when you're dealing with variance, it's kind of like there's no granularity to it. You're putting in a pretty low variance value to include a pretty large scope of interfaces as long as they meet the feasibility condition. Okay. So with RIP, okay, we do only equal cost load balancing. But the problem with RIP is that the metric that's used has nothing to do with bandwidth. The metric for RIP is hop count. So if the top path has 5 hops and the bottom path has 5 hops, then both paths are going to be used. However, bandwidth is not considered. So if the top path is a gig and the bottom path is 100 meg, we're going to get something called pinhole congestion, where basically we're doing per packet load balancing, but we're taking the least common denominator, if you will. So the 10 meg or the 100 meg connection is going to be kind of the maximum bandwidth limit for both links. So my gig interface or my gig link is going to end up looking like a 100 meg link because I have to kind of equally share the traffic over those two links, even though they're not the same bandwidth. That is a concept in EIGRP called pinhole congestion. With EIGRP, it does smart load balancing. It has the ability to differentiate the circuit paths and say, you know what, these paths are not equal, even though we're treating them as equal. So I'm going to distribute the traffic load across these links in an appropriate manner so that all the links are utilized to their most efficiently. Okay. It says here, EIGRP not only provides unequal cost path load balancing, but also intelligently load balances with traffic sharing. All right. And we use the command traffic share balanced to distribute traffic proportionally to the ratios of the metrics that are associated to the different routes. That's the default, by the way. Traffic share balanced would be the default. If I go into my EIGRP configuration and I say traffic share min across interfaces, then we send the traffic only across the minimum cost path, even if we have multiple paths in the routing table. I've never used that option before. There's really no need to, but let's go ahead and describe how that works, right? So we have 3 paths to network X. Now, which one of these paths is my successor? It would be the middle path through router C, right? Because the feasible distance of that path is 20. Make sense? The feasible distance of the top path is 30. The feasible distance of the bottom path is 45. So I have a range of 20 to 45. What kind of variance would I have to apply to make sure that all 3 paths are used? I would have to have a variance of 3, right? Because I'd have to go from 20 to 60. If I had a variance of 2, that would only allow 20 to 40, which means that the path through the bottom router, router D, would not be used. So a variance of 3 should give us the ability to load balance across all 3 paths. However, is that going to be the case? If I put in a variance of 3, I know that anything from 20 to 60 now is going to be considered equal. But are all 3 paths going to be used? And the answer is, ding, 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 no, right? Only 2 paths would be used. Why is that? All paths fall within the variance, 20 to 60, because we used a variance of 3. But only the path through router B and C would be used. The path through router D would not be used, because router D does not meet the feasibility condition. The reported distance from router D is 25. 25 is higher than 20. The reported distance of the path through router D is higher than the feasible distance of my successor path, which means that the path through router D does not meet the feasibility condition. Even though it might fall within the variance, it cannot be used because we don't know if that is a loop-free alternate path. We haven't guaranteed that because of the metric. All right. So they kind of go through the scenario here. In this case, we already know that the bottom path would not fall within the variance, even if we had a variance of 3, because of the feasibility condition check fail. So in this case, they've applied a variance of 2. Router E chooses the path through ECA. originally because that path has a metric of 20. So 20 is better than 30, it's better than 45, right? Makes sense. In order for us to go ahead and make sure that we also want to use the path through router B, we have to have a variance of 2 because the path through router B has an overall feasible distance of 30. 2 times 20 is 40. And we can't do fractions, by the way. We can't say multiply it by 1.5 or multiply it by 0.8 or whatever. It has to be whole numbers. So I can either do 1 or I can do 2, which means 20 through 40. All right, so by applying a variance of 2, we take the best metric, multiply that times 2, which is 40. Now we're going to include all the routes that have a metric of less than or equal to 40 and consider them, that meet the feasibility condition, that's very important, and consider them equal cost. So we have now 2 paths to get to network X. We can go through ECA or EBA because both of those path metrics are under 40 and they both meet the feasibility condition. EDA has a metric of 45. So we already know it's not going to qualify anyway because it doesn't meet the feasibility condition, but we also know it doesn't fall within the variance. So not only do we not meet the feasibility condition, we don't fall within the variance, so the route's just simply not going to be used, if that makes sense. All right. The reported distance, remember, of that neighbor is 25, so that doesn't meet the feasibility condition. And that's what they're saying here in this last part of the paragraph. EDA is not selected in load balancing because router D is not a feasible successor. Now, to control how traffic is distributed among the routes, when there are multiple routes for the same destination that have different costs, unequal cost load balancing, we use the traffic share balanced command. Like I said, with the balanced keyword, we distribute the traffic proportionally using different ratios. This command you don't actually have to put in because that's already done by default as part of the overall process, right? So traffic share count, it ends up being kind of a ratio, if you will, of the number of packets that I'll send. So it might be like 4-to-1 or 3-to-1 or 2-to-1. It's a little bit more complicated than that when it's calculated. And it's a whole number. It's we don't do any floating point math on these calculations as well. So it says here, for the path from E to C to A, we have the alternate path metric, which is 30. And the overall path metric for this particular path is 20, which means we're doing a 3-to-2 load sharing. 3-to-2 is not a whole number, so we round it up to 1, right? For the second path, E to B to A, the alternate path metric is 30. I am the alternate path, and my path metric is 30, which is 1. So in this particular case, we would actually not really do any kind of balanced load sharing because of the way the math works. If it was more different, right? If there was some, the calculation was like 40-to-20, which is what we see here. 40-to-20 would be 2, and 40-to-40 would be 1. So this would be my successor path is 20. Maybe I have a variance of 2 in this case. So anything from 20 to 40 is considered equal. So it's kind of like in this case, for every 2 packets I send on this path, I would send 1 packet on this path. That's the ratio concept that I was talking about earlier, is what you kind of see in that scenario. All right. If I use the traffic share min, the traffic is sent only across the minimum cost path, even if there are multiple paths in the routing table. And like I said, we don't typically, I've never used that option in the configuration. That means that we're basically only going to send traffic through ECA, which almost kind of eliminates the whole concept of load sharing anyway. All right. The only difference here is that the other routes get installed in the routing table. They're just not used, but they could be used if the primary route fails without having to really do any kind of reconvergence. What is the default variance for EIGRP unequal cost load balancing? The default variance is 1, which means only ECMP is going to be used. Unequal cost load balancing is not an option. All right, not 2, 1. Now, the wonderful thing about all the stuff that we've learned up to this point is that when we move to IPv6, all that theory stays the same. Successor, feasibility condition, metric calculations, everything is exactly the same. It all works the same way. So you don't have to relearn the whole protocol all over again if you're moving from IPv4 to IPv6. That's a wonderful thing, okay? Implementation is slightly different, right? In IPv4, we start the routing process globally by using the router EIGRP command. We put in network statements to include the interfaces that we want to run the protocol. We do our metric weights, we do our variance, we do maximum paths, all that stuff under the routing process. For IPv6, we still have to enable the routing process globally using the IPv6 router EIGRP command, but we don't use network statements. We implement the protocol directly on the interface as opposed to using network statements. So it's very easy to configure. Everything that we talked about with regard to IPv4, the fact that it's advanced distance vector, that it has this protocol-dependent module support, or what we call PDM support, adjacencies, the message types, hellos, updates, queries, replies, all that stuff is the same for IPv6. None of that stuff changes. Certainly the addressing component changes, right? Neighbor discovery in IPv6 uses link local addresses. That's a special type of address in IPv6 for communicating across local wires with an FE80:10 address. We still use dual. We use multicast to send out and propagate information. In the case of IPv6, it's FF02:A. FF is multicast. All IPv6 multicast addresses start with FF. 02 defines the lifetime and the scope of the multicast address. 0 means that it's a well-known address, meaning it's permanent. And 2 means that it has a link local scope. So it's a non-routable multicast packet. And then the :A is the group number, the IPv6 multicast group number. All right. But it's the same concept. I send hellos to form adjacencies. The same parameters exist in the hello packets as we saw in IPv4. So we have K values, same metric calculation. Load balancing, equal and unequal cost load balancing is available. We still have a neighbor table. We still have a topology table. The concept of successor and feasible successor is identical. So everything is pretty much the same. We still use bandwidth, delay, reliability, and load as part of the metric. We still have K1 and K3 as a 1, and K2 and K4 and K5 are a 0. We still have the ability to use wide metrics versus narrow metrics if we're doing classic EIGRP configurations or address family EIGRP configurations. So it's not different. Everything is pretty much the same. All right, I'm not going to read this whole section here because that's essentially what they're describing. But hopefully when we get into our advanced routing section, we'll be able to see, kind of those slight differences with IPv6. If I want to verify my adjacencies in IPv4, I do show IP EIGRP neighbors. Okay. If I want to do the same thing in IPv6, show IPv6 EIGRP neighbors. If I want to see my topology database, show IP EIGRP topology. If I want to see it in IPv6, show IPv6 EIGRP topology. So it's, it's very, very simple to kind of transition from v4 to v6. All right. All right. So comparing EIGRP and the OSPF routing protocol, right? Later on, we're going to be talking about OSPF, and we're going to get into a bunch of details about OSPF and what's involved. But, the protocols are significantly different with regard to how they function. Obviously, one is a link state routing protocol, that being OSPF. The other is a distance vector protocol. The setup of EIGRP is relatively simple, mainly because EIGRP operates in a flat design, right? OSPF, excuse me, operates in a hierarchical design. It can be implemented in a flat architecture if you just do a single area OSPF, but most people that choose to implement OSPF will use the hierarchy, the spine and leaf hierarchy, to implement it. But the protocols themselves are relatively simple to implement. EIGRP certainly very easy to implement. The design of EIGRP is very flexible. And what they mean by that is that with EIGRP, we have the capability of implementing summarization arbitrarily in the topology. We can choose to summarize at any point in the network, whereas OSPF, we can only summarize on ABRs and ASBRs, and we have specific area designs that we have to take into account with regard to how many routers can exist in an area, how those areas can be interconnected, and so on. But with EIGRP, it's implemented as a single autonomous system, so it's a very flexible design in that regard. Scalability, medium to large with EIGRP. If you implement things like summarization and query scoping in EIGRP, it can scale to a pretty large environment, whereas OSPF scales to a really, really large environment, especially if you implement the spine and leaf design with the multi-area implementation, all right, which we will talk about later on. As far as processor requirements, EIGRP is a pretty efficient protocol. It doesn't require a whole lot of resources because it's a distance vector protocol, so it doesn't keep a complete picture of the topology. The topology database is relatively basic compared to OSPF, which keeps a very detailed topology of the or information about the topology of the network itself. Being that it is link state, it's going to maintain detailed information about every link in the topology, which, by the way, can be a significant amount of information, especially if you have a lot of nodes on the network and you have a lot of links between the different nodes. Provider support, less likely with EIGRP because predominantly it's still proprietary, even though it's been released as an open standard for the most part. A lot of vendors still have chosen not to adopt EIGRP as a protocol that they implement on their platforms, right? I mean, Juniper's not going to be, chomping at the bit to get EIGRP put on their network in their topology, in their operating system, in their code. So there's still going to be kind of limited support for EIGRP on multi-vendor platforms. We talked about the concept of equal versus unequal cost load balancing. Both IPv4 and IPv6 are supported on EIGRP in classic mode and named mode configuration, and OSPF v3, traditional implementation of OSPF v3, or using OSPF v3 where we use address families and we actually use IPv6 as the primary transport to transport not only v4 information but v6 information within OSPF. That's a concept that we'll talk about later on when we get into the OSPF section a little bit later on. So the first thing to consider if you're deciding to use EIGRP or OSPF is do the devices that you have in your topology support the protocol itself. Do you have an understanding of how the protocol works? Of course, we want to make sure that we have a vast understanding about how to implement the protocol, how to implement the features within the protocol? Do we understand what the impact is of implementing specific features of the protocol within our topology as well? Even though EIGRP is a standard today, only a few vendors have decided to incorporate it in their operating system, right? I believe HP is starting to incorporate it, but Juniper, with their operating system and their focus on open standard protocols, is probably not going to be jumping at the chance to include EIGRP within their design anytime soon. All right. The last thing we look at here is the chart that kind of describes the scalability of the protocol from a convergence standpoint. And we can see that, relatively speaking, I mean, if we're talking about a realistic network design, scalability is not really much of a concern with OSPF or EIGRP. We're talking about, thousands of routes, and not a lot of enterprises or organizations are going to have thousands of routes within their architecture. But as I go up to 5,000 routes, we can see as long as I have feasible successors, as long as I tune OSPF, maybe implement things like OSPF LFA and tune the timers within OSPF, there is very minimal effect on adding thousands and thousands of routes into the topology. But if I'm running EIGRP without feasible successors, or if I'm using OSPF with default values, we can see that the convergence time is pretty significant compared to the other option as the number of routers increase, especially with EIGRP. That orange line that kind of just shoots up there is what happens if you have a large query domain. That's really what they're kind of referencing here. I lose my successor route. I don't have a feasible successor. That means I have to send queries out. That orange line kind of represents the impact of those queries across the topology, if that makes sense. All right. So just a kind of a side-by-side comparison of each of the protocols. So what is impacted in EIGRP as the network gets larger? Bandwidth utilization, convergence time, routing tables, or all of the above? I would say in this particular case, all of the above. With bandwidth utilization being kind of the smallest impact, the number of routes being the largest impact, assuming you're not doing summarization and you don't have summary boundaries in your topology, and convergence time kind of being in the middle there. Again, I mentioned this kind of when we started this lesson. I said, look, you can choose routing protocols that are inherently going to be better. They're just, by their overall design and their overall implementation, they converge faster, they operate more efficiently. But just like anything, there's a good way of implementing something and there's a poor way of implementing something. So not only is it just a matter of choosing the appropriate protocol, it's a matter of choosing to implement the protocol correctly. And it's not just a matter of put in these commands and make sure everybody has adjacencies. Plan out your summary boundaries, plan out where you're going to add efficiencies to the design by limiting the scope of queries in the topology, or limiting the number of prefixes that might exist in the database by including nice contiguous blocks of addresses that can be summarized, and so on. So a good addressing plan is required, a good overall design is required, and so on. All right? Definitely something to consider when you're implementing these protocols. So let's go ahead and wrap up this section here by going through our summary challenge. Which two options are classified as link state routing protocols? That would be ISIS and OSPF. These are link state protocols. EIGRP is considered to be a hybrid protocol, but fundamentally it is still distance vector. It does take a lot of characteristics of link state, but it still doesn't have a complete picture of the topology, so it's still considered to be a distance vector routing protocol. RIP is considered to be a distance vector, and BGP is classified as a path vector routing protocol. Although if you look at BGP from the perspective of autonomous system routing, it's kind of like a distance vector routing protocol in that it routes to autonomous systems as if they are hops in the topology. But generally, BGP is considered to be a a path vector routing protocol. All right, and we'll get into that in a couple of lessons here. We're gonna be doing our eBGP discussion. A router has learned 3 possible routes that could be used to reach the destination network. One route is from EIGRP and has a composite metric of 205.84570. Another route is from OSPF with a metric of 842. The last is from RIP version 2 with a metric of 3. Which of these routes is going to be installed in the routing table? Now, it's interesting that they ask us this because we discussed this concept, right? We talked about administrative distance and how protocols are designed or categorized based on administrative distance. But we didn't see anything in the book in relation to that, right? There was no discussion of that in the chapter. But given the fact that EIGRP has an administrative distance of 90, and OSPF has an administrative distance of 110, and RIP has an administrative distance of 120, we know that the EIGRP routes are the ones that are going to end up going in the routing table. The actual metrics themselves don't really come into account. They don't matter because ultimately we're not comparing metrics. We only compare metrics if the route's being learned by, if the same route is being learned by the same information source, meaning that we're learning about the same destination via 2 EIGRP nodes or whatever it might be. Refer to the figure and the output of the show IP protocols command. Which 2 EIGRP metrics are being used to affect the calculation that selects the best path? So if you look at the output here, we see the metric weights. The metric weights is what's tied directly to the variables within the metric. K1 is equal to 1. K3 is equal to 1. The rest are 0. K1 corresponds to bandwidth. K3 corresponds to delay. So that would be my answer in this case. Bandwidth and delay are the 2 components. Which 2 of the following commands should you use to determine whether the EIGRP router ID has been configured in the EIGRP process? Now, again, not discussed in the chapter, but the router ID can be configured in one of 3 ways. And these will be listed in the order of preference, or the order of priority, I should say. So the first option is to just simply manually configure the router ID. And you do that under the routing process. You go into router EIGRP 1 or router EIGRP 100, and you simply say EIGRP router ID and put in a 32-bit dotted decimal number. Doesn't have to be an IP address, but it does have to be in a dotted decimal format. Okay? If the router ID is not manually configured, then the router ID is selected based on the highest loopback IP address. Not the highest loopback number, but the actual IP address. So if I've got loopback 0 that has an address of 1.1.1.1 and loopback 10 that has an address of 2.2.2.2, then the router ID would become 2.2.2.2 because it's higher than 1.1.1.1. If I don't have any loopback interfaces and I haven't manually configured the router ID, then the router ID is selected based on the highest physical IP address. And again, it doesn't have to be an address that's part of the EIGRP process. It just has to be an address in general, right? So in this case, if I want to determine how the router ID was configured, I could certainly do it by running the show IP protocols command. In fact, we'll scroll up and take a look here. You can see, actually we don't see it here, which is oh yeah, here it is, sorry. Here's the router ID. Now it doesn't tell me how it was set. It tells me what it is, the router ID, but that could have been manually configured or it could have come from an interface. So it would have to be kind of a combination of a couple of different things, right? You'd have to look at show IP protocols, number one, to see what the router ID is, and you would probably use a show IP EIGRP interface to see the IP addresses of the interfaces and to see what interfaces are running EIGRP. Again, it doesn't really matter that they're running EIGRP, but I think what they're asking in this particular case is what two commands in combination would allow me to identify how the router ID had been established. I would say certainly show IP protocols will tell you what the router ID is. I still couldn't assume that it was automatically selected, though. Even if I have an interface with that address, I still could have manually configured the router ID. So I don't necessarily kind of agree with this question, how it's worded, but that's a standard Cisco thing. Okay. What does passive interface command do? We talked about that as well as part of our discussion. Passive interface allows a network on an interface to be included in the routing process. In other words, it allows the network to be advertised. However, it suppresses the protocol on the interface. If I just simply implement a protocol and I exclude the network on an interface from the protocol, then it won't be advertised to the rest of the peers in the network. So in order for any network to be advertised, it has to be part of the routing process. The interface has to be part of the routing process. But maybe it's a LAN interface that goes to different clients on the network, but there aren't any other routers on that interface that need to see routing information. So there's no reason that I would ever want to send hello packets out that interface because there's nobody there to see those hello packets. And not only is it a waste of resources to send those hello packets on a periodic basis, but it could actually be a security risk, right? Somebody could capture that hello information and they can infer quite a bit about the topology from that hello information, which is multicast, which unless you're running something like IGMP snooping on your network, is going to get flooded within the broadcast domain anyway. So it would be very easy to capture that information. All right. So what passive interface does is it allows me to include a network statement for a particular interface so that I can advertise that network to the rest of the world, but it suppresses the protocol from running on the interface and suppresses the protocol from sending hello packets and so on. So let's see, the answer, the router cannot form adjacencies. That would be true, right? I only send routing updates if I have a peer. So regardless of whether or not passive interface is configured, if I don't have a neighbor relationship on a particular interface, I'm not going to send routing updates out that interface. But I can't even form an adjacency on an interface that's passive because I'm not sending hello packets. So there's no way for anybody to discover that I exist, which means I can't form an adjacency. And if I don't form an adjacency, then I can't exchange information. So that would be the best answer, A, is it's just not going to give me the opportunity to do anything with a peer on that particular interface, if that makes sense. All right?
Hey, Scott. So they have an answer key for this?
Yes.
And they actually, the question before this and this question, they do not align with what you chose.
Okay, well, let's talk about that. What is the one before this? What did they choose?
They chose show IP protocols and show IP EIGRP topology.
Okay, I could see, let's talk about show IP EIGRP topology, right? So it's the question says, which of the two following commands should you use to determine whether EIGRP router ID has been configured in the EIGRP process? All right. So how would show IP EIGRP topology show me that information? The only thing that you can infer from show IP EIGRP topology is which interfaces are actually running EIGRP. Okay. And I'm not talking about the networks that are not attached, the networks that I'm learning, or the networks that I'm learning from other peers. Even connected routes would show up in the topology database if those interfaces were running EIGRP. But
so if you do a show IP EIGRP topology, the very first line that it provides you is the topology table for your AS number.
Correct.
And router ID.
Correct. It will tell you what the router ID is, but it doesn't tell you how it's set. See what I'm saying? The question says, which commands should you use to determine whether the router ID has been configured? Okay, so I guess I'm reading it differently, right? I'm reading it as, because look, a router ID is always going to exist, no matter what. You turn on EIGRP for IPv4, and a router ID will always be set, period.
Right.
So the way I interpreted the question is, was it set manually? In other words, did you configure it manually? So again, that was just kind of a misinterpretation of what they were asking there. But so what they're basically saying is, which commands will let me see what the router ID is? And that is correct. The topology command and the protocols command will show you actually what the router ID is. But it doesn't show you how it was set. All right. The next one you said was they had chosen a different one as well.
It chose the bottom answer.
I didn't actually get down to reading that one, so let's see what it says. It might actually be a better choice. The passive interface command in EIGRP suppresses the exchange of hello packets between routers, which results in the loss of their neighbor relationship, and it does suppress incoming routing packets. So both of those answers are correct then, right? A and D, because if I can't send hellos, I can't establish an adjacency. Thankfully, the questions on the test are not like this, but yes. I guarantee you that a router cannot form neighbor adjacencies on an interface that's passive. Because it's the protocols, the hello packets are being suppressed. Even if I did a manual neighbor statement, the hello packets would be suppressed on a passive interface. So A is true, but so is D. All right.
Yeah, they like to trick us with those sometimes. That's why.
Even C is true, right? Actually, they're all true, but they're not complete, I guess, right? A router cannot send routing updates on the interface is true. Passive interface, I'm not going to send routing updates because I can't form an adjacency. Passive interface, I'm not going to receive routing updates because I cannot form an adjacency. So those are true as well, but I guess D is more true because it more specifically defines why, I guess, is the point. So I probably would have chosen D had I gotten down to reading that one, but technically all these are true in that regard. Here is a show IP route command on router 1, which is load balancing to the 10.80.13.0 subnet. All right. So we can see that we've gone through 234.3 and 234.2 with the same metric, 268.1856. On router 1, the following change was made. In which two ways will the routing table and topology table be affected? So they did a maximum paths of 1, which means that load balancing is no longer permitted. We're only allowed to choose one path. So it says there will be no change in the routing table. That's not true. The EIGRP topology table will indicate both routes to the network, which will be true. Both routes will still be there in the topology table because they're both valid routes. There's no doubt about that, right? They're both valid routes. They both are allowed to be learned because, again, in the topology table, we have everything that we know. The EIGRP routing table will only have one route for 13.0. That's true as well. So this one and this one. The EIGRP topology table will only have one route. That's not true. Or it will have no routes. That's not true. So hopefully that's what they have in the answer key this time, because that's what is true. That's what would happen. Since you're looking at it, Charles, is that what they have?
That's what they have.
Yeah. Yeah, there's really no kind of misinterpretation here. Just because we're doing maximum paths does not mean it doesn't go into the topology table. Maximum paths only affects what goes into the routing table. Now, as far as which route will be used, that's a little bit more complicated because there are some kind of internal processes that are used to determine which of those two routes will be chosen. And I'm not completely versed on what that process is, but it's not just arbitrary. It will pick one of those routes for a particular reason. Refer to the output of the show IP protocols command. Which statement is true about the routing configuration? Well, as I scan through this, we're using EIGRP Autonomous 65010. We're not doing any route filtering. We have our default K values. The router ID is 172.16.1.1. Administrative distance values haven't been modified, 90 and 170. Maximum paths is the default, which is 4. The variance is 1, so only equal cost load balancing. Automatic network summarization is disabled, so no summarization to major boundaries. So it looks like kind of a standard EIGRP configuration. Let's see what the question says. The router is configured to load balance over unequal cost paths. We know that's not true because this variance value would have to be something other than 1. The router is configured per destination and per packet load balancing. I'm not sure how you would determine that from this output. Load balancing would be allowed because we do have a maximum paths of 4. So as long as the paths are equal cost, that would be true. We would, and we had multiple paths, we should be able to load balance. The variance is set to the default value of 1, which requires all the paths to have the same cost to be eligible for load balancing, and that's absolutely true. The router is configured with automatic summarization. No, automatic summarization is disabled. So in this case, I would say C is the best answer. The per destination, per packet load balancing might be true, but there's no way to really confirm it from this particular output. We know that load balancing is going to happen if I have equal cost paths. But again, C is probably a better answer in this case. It's more specific and it's 100% true. So that's what I would pick in this case. All right. Besides EIGRP, which other protocol supports unequal cost load balancing? None of them. No one does. BGP doesn't even do load balancing. RIP, ISIS, and OSPF can only do equal cost load balancing. All right. I mean, you can technically achieve unequal cost load balancing in those protocols if you trick the router into thinking the paths are equal. That's one way that you can do that. You can trick the router, but then you're kind of doing inefficient routing in that sense because the router is going to treat the paths as equal even though they're not. Which of the following correctly describes an EIGRP feasible successor route? A backup path, a shorter path, a suboptimal path, or the best path. A backup path would be the choice that I would choose. The shorter path would be the best path. And a suboptimal path, well, it is, I guess, technically suboptimal compared to the best path, but it is the backup path. When should you enable the EIGRP load and or reliability metrics? Only on core routers, if needed for troubleshooting, to identify better paths when load and reliability change under recommendation by Cisco. I would say D, because just about all the documentation from Cisco says don't ever change the values. Okay, so I would say D is probably the best choice. Charles, is that what they chose?
Yes.
Yeah. And Cisco is probably never going to recommend that. So if there was a choice of never change it, that's the one I would choose. But D is the best choice in this case. Which two options are classified as link state protocols? So we're back into our repeats now. All right. So that wraps up our lesson on EIGRP. We managed to cover it in less than 3 hours. That's good. Let's go ahead and wrap up this section and go into some OSPF.